Statistical signal processing. We have 4 talks in this session, and the first speaker is Po-Ling from the University of Wisconsin.
Okay, well, thanks very much, Ramji, for the invitation to be here. It's really an honor to be at this conference. I'll be talking about some work with my colleague Varun Zog. It's about a teacher-student learning problem. Actually, Varun was working on this problem for a while, and I joined more recently and added some extensions. So the setup is social learning. So you have multiple people who are trying to infer something about the state of the world from listening to noisy observations from each other. And here we are looking at a very, very simple setting where there are just 2 agents. There's a teacher and there's a student. And the setting is that the teacher, every day for n days, observes an IID observation that's some noisy version of the state of the world. And for the first part of this talk, the state of the world is just binary. It's either a +1 or a -1. And the teacher observes these IID observations pass through a binary symmetric channel where the error probability is p. And the student receives some sort of a lesson from the teacher. And we're going to discuss different strategies for how the teacher prepares the lesson and how the student then infers what her estimate of the state of the world is. So for instance, the teacher could be super lazy and just say whatever noisy observation he sees of the state of the world on each day, he just simply forwards that straight to the student. So that's one example of a lesson. Another example, which we'll call cumulative learning, is where the teacher keeps on updating his guess of the state of the world and then passes that along to the teacher, passes that along to the student. So every day, this is now no longer an IID observation. It's sort of a cumulative guess over the time that has passed so far. We want to understand, for different combinations of teacher strategies and student strategies, what is the learning rate that the student will incur in trying to learn what theta actually is. So we will characterize the learning rate, where the learning rate is defined in this way. So you look at the error probability as a function of the teacher and student learning strategies and as a function of n. And for instance, if the teacher was doing cumulative learning, so the teacher keeps on updating some best estimate of the state of the world, then as time progresses, the teacher will eventually learn the state of the world and keep on transmitting +1 if the true state of the world is +1. And the teacher will learn this at an exponential rate. And this is why we want to look at taking a log of the error probability and dividing it by n and looking at the limit there. And so, as I said, we'll be interested in sort of analyzing the best strategy for the teacher and the best strategy for the student. And since we're looking at error probabilities here, it's not too hard to convince yourself that if you fix what the teacher is doing, then the optimal student strategy is to be a Bayesian learner, because the student is trying to minimize the probability of error over all possible strategies. However, in the social learning literature, it's not, well, one doesn't always want to assume that Bayesian learning is what's going on. So partly that's because assuming that everyone can be a Bayesian learner is assuming that everyone is completely rational, and that's maybe not a good assumption. And also, it can be hard to actually compute what these Bayesian updates are, which is also why people aren't necessarily Bayesian learners. And lastly, if we want to characterize this precise error rate, then that might not be very easy to compute in the case when we're doing Bayesian learning. Okay. So what we're going to do is try to analyze what this R is with respect to some more simple teaching and learning strategies and see if we can get some insight for when the teacher should actually be learning some sort of, doing some kind of special learning and teaching a lesson, or just simply forwarding information. And what we'll see is that the strategy that the teacher or the student should employ will depend on these error flips, on these channel probabilities. Yeah. Yeah, so we're going to be assuming that the student and the teacher are aware of, well, there's sort of 2 settings. So one is where the teacher is passing their best guess and the student is just taking a majority vote. And there, I mean, we're assuming, we're going to analyze this for a pair of teacher-student strategies. Then there are more complicated strategies where the teacher and the student will be sort of tuning their strategy according to what they know the other person is doing, and also these error probabilities. And I'll kind of unwrap that as we go along. But yeah, so the best strategies will depend also on what these parameters P and Q are. So how good is the teacher and how good is the student? Okay, so, well, I'll repeat this notation as it becomes relevant, but roughly speaking, the teacher observes Y and transmits X, and the student observes Z. And we'll be interested so x hat is the teacher's lesson, so that's going to be a plus or minus 1. And we'll also be interested in the cumulative sum of what the teacher observes. So the teacher is observing plus or minus 1s and basically seeing a random walk. And we'll be interested in understanding, well, what is the teacher's best guess? So if the teacher were to transmit the best guess, then what would that look like? So that's what this, the xn will denote. Okay, so there are sort of two student strategies that we'll analyze. The first one is just the majority vote. So remember, the student is observing these zi's on each time instant. And the simplest student strategy is that regardless of what the teacher is doing, the student could just do a majority vote over all the observations over n time steps. And then there's another student strategy that we'll also be interested in analyzing. And this is the epsilon majority rule. So basically what the student will do is they're going to be looking at just the last epsilon n time steps and averaging majority vote over those last time steps. And what's the rationale behind this? It's that, well, a very skeptical student would say, okay, the teacher is also learning as time progresses. And if the teacher keeps on updating their best guess, then maybe the first chunk of time is going to be kind of noisy, so I'm just going to not pay attention. So then this is what we call epsilon majority, just weight those last epsilon n time steps equally. Now, you could think about cases where the student is sort of doing a majority vote and the weight is increasing as time passes. So it's not just 0 or all the same, but it's something more gradual. The reason we don't analyze this is, again, it gets more and more complicated to characterize what this learning rate is as you get a more and more complicated strategy. Okay, so these are the two that we focus on. Then for teacher strategies, we want to get some insight in terms of should the teacher actually be doing some effort to prepare a lesson based on what he's seen, or should he just be simply forwarding information? So one kind of baseline strategy for the teacher is just whatever he reads the night before class, he transmits that. And then, of course, the student observes that with the probability Q of noise, probability Q of error. Then the other strategy we've discussed is this sort of cumulative strategy where the teacher is, in fact, forwarding his best guess of the state of the world. So he looks at his sign of the random walk, which tells him, well, how many plus 1s and how many minus 1s has he seen? And if it's positive, then he'll transmit plus 1, otherwise minus 1. And then, motivated by this epsilon learning strategy, where the student is just looking at the last epsilon time steps, then we also analyze sort of an intermediate strategy, where the teacher says, okay, so now the teacher is aware that the student is going to be an epsilon learner and is just going to observe those last epsilon time steps. So a teacher who is sort of diligent and sort of lazy would say, well, for the first 1 minus epsilon times n time steps, I'm just going to transmit something like, let's say, plus 1 all the time. And then in the final epsilon n time steps, when I know that the student is paying attention, I'll just take my best guess after the first 1 minus epsilon n time steps, and I'll transmit that repeatedly. Okay, so it's like teacher learns for a while, stops learning, and then just transmits. And we don't expect that this will do as well as cumulative teaching, but the nice thing is we can also kind of characterize the rate of learning for this and see just how much worse this is than, for instance, a cumulative teaching strategy. Okay, so I'm not going to have much time to talk about proofs in this talk, although I'll try to talk about some a little bit. But the next couple slides, I'm going to give you kind of a pictorial preview or overview of what the main insights are from our analysis. So there's this plot, and this plot is saying, if we fix the student strategy, so if the student does the most simple thing, which is just to be a majority learner over n time steps, what should the teacher do? Okay? And I'll remind you that the things we discussed the teacher might do are, let's ignore the last one for now, because the student is going to look at all n time steps. So just deciding, should the teacher be simply forwarding or doing cumulative teaching? Okay, so what you might think is that, well, of course the teacher does better if they're actually forwarding the best guess rather than simply forwarding information. And that's wrong. So in this picture, we see the regions, and this is a function of P and Q. So P is the probability of error for the teacher observing, for the teacher's channel. And Q is the probability of error for the teacher-to-student transmission. And as I said, the best strategy and the learning rate in general will be characterized by this pair P and Q. How good is the teacher and how good is the student? And what we see from this picture is that if the teacher is lazy and simply forwards these observations straight to the student, then there are pairs of P and Q, in particular the blue regions, where it is actually better to simply forward. And this might be kind of surprising, and to sort of try to interpret the result a bit further, we can think about what happens if we just imagine looking at a horizontal cut of this plot. So what that means is that we fix the channel for the teacher. So the teacher is going to have some probability of observing with noise. This is something between 0 and 1/2. All right? So we look at some cut, and then we say, well, as a function of how good the student is, should the teacher be doing a high-effort strategy of cumulatively learning, or simply forwarding? And what we see is that for small values of Q, meaning a very, very smart student, what the teacher should do is simply forward observations, rather than saying, let me forward my best guess, okay? And why is that true? Well, basically, remember that we have fixed the student strategy, and the student is going to be doing a majority learning algorithm over everything that she sees. So if the teacher is observing this random walk with some noise, then there's some reasonable probability that the student will just see a lot of bad observations that are all in the negative direction, and it will take him a while to recover. And therefore, it would be better for the student to not get misled and equally weight all of these observations. So that was sort of an interesting insight. And I think the other interesting insight was that we could actually characterize what the learning rate is, but I'll get more to that later. And then another interesting observation from looking at this plot is that now if you imagine sort of going across in these slices, but you imagine different slices, then one thing to notice is that if you draw a vertical line, then there's a point at which everything is yellow. Which means that if the student is not a perfect learner, so if there's some probability that the teacher-to-student channel, those bits get flipped, and that probability is at least something like 0.15, then it's always better for the teacher to do the cumulative teaching strategy. All right? So only for very sharp students would it be good for the teacher to be lazy. Okay, and then we were thinking about another strategy, and the other strategy was where the student is not just averaging everything that she sees, but averaging just the last bit, the last epsilon n time steps. And not surprisingly, if the teacher is learning cumulatively rather than stops learning and then only transmits the same observation in the last epsilon n time steps, then one can show that the learning rate is in fact higher for cumulative learning. And then the other thing is that if you also look at the same kind of plot, but this time, remember, the student strategy is different. It's not just majority vote over everything, but majority vote over the last epsilon n time steps, then there are still settings in which the teacher is better off simply forwarding. So this plot is very much like the last plot, except now the region in which simply forwarding is better is smaller. Okay, and then there's kind of the last part of the talk will address the Gaussian learning setting. So everything I've said so far is assuming that the state of the world is binary. It's either a +1 or a -1. But one might think, well, what if the state of the world is some real parameter? And instead of doing majority voting, the student is doing something like averaging all of the time steps, right? And actually there, everything turns upside down. So in that setting, using the color coding of this figure, it would all be yellow. Or sorry, no, it would all be blue. So it's actually better to be simply forwarding. So that's just completely the opposite of what we see in the binary case. Okay, so now I'm going to talk a little bit about some of the math behind what's going on. I'm probably going to give you an abridged version, but let's at least get started on this. So let's imagine the case where we're analyzing simple forwarding and majority learning. Okay, so the teacher is not doing anything to his observations, and instead he's just forwarding them straight on. So that's like the easiest case, because if you just look at things from the student's perspective, she is simply receiving observations of the state of the world through a binary symmetric channel, where the error probability is now something different, which is a function of both P and Q. Okay, and so she is receiving these IID observations passed through a binary symmetric channel, and it's not too hard to see that, in fact, the learning rate can be characterized as the KL divergence between this parameter of the binary symmetric channel and the Bernoulli 1/2 distribution. Okay, so this is, and I won't be commenting more on this, but we can use this sort of as a baseline to compare all of the other harder methods of learning and teaching. Okay, things get more interesting if we start looking at more sophisticated methods of teaching and learning. So imagine the setting where the teacher is doing cumulative teaching. So he's forwarding on his best guess of the state of the world. And now the student is doing majority learning. Okay, so in this case, what do we care about? Well, as I said, we want to see what the teacher's guess is that he is passing on each time. And that will depend on his random walk, which is going +1 wherever he saw a +1 and a -1 otherwise. And we call x hat the lesson that he is transmitting to the student. So what will characterize an error is when, so let's imagine for now that the student is a perfect learner, so there's no noise in transmitting from teacher to student. Then an error occurs if this random walk happens to be positive less than half the time, right? Because the student is just going to do a majority vote over the observations that she received from the teacher. And the teacher is simply sending along the sign of this random walk on each time step. Okay. So we need to understand, well, what exactly does this random walk look like? So this random walk is going upwards with probability 1 minus p and downwards with probability p because it's a binary symmetric channel. And the trick ends up, in analyzing the learning rate, it ends up being a characterization of the sign of this random walk by breaking up the analysis into what's happening in between return times to 0. Okay, so I'm just going to give you a taste of what this sort of looks like. So you can first ask yourself, well, how many return times are there to 0? So it turns out that's a geometric random variable. Because remember, this random walk is going up with probability 1 minus p and down with probability p. And you can check that the probability of returning to 0 from a particular time step is going to be 2p. And then there's going to be some probability that's going to run off to plus infinity. It won't run off to negative infinity because it's biased in the upward direction. So we're assuming that the probability p that the teacher observes with an error is less than 1/2. Okay, so now we have to ask ourselves, well, okay, so if we were to generate a geometric random variable that would tell us how many times we return to 0, well, we don't just care about how many times we return to 0. We want to know how many times will we be above 0 and how many times will we be below 0. Because at the end of the day, we care about this signed walk, right? How much time is spent above and how much time is spent below. Okay, so it's not too hard to see that you can calculate the probability that the length of a sojourn in between positive and negative times has this distribution. Except there's a typo that I noticed this morning. There should be absolute values in the exponents of the p and the 1 minus p. Where does this come from? Well, so okay, if your length is 2k, then you go up k times and you go down k times. So that's the p to the k times 1 minus p to the k. And then you also have to look at the number of paths there are that stay entirely above or, let's say, entirely below the axis, and that's given by the Catalan numbers, and there's a nice expression for that. So that's basically where this formula is coming from. I put in parentheses signed. Okay, so signed, it means that, well, it either went up or it went down. All right, so when we do actually care about tracking, did it go up or did it go down? Because we want to know when was it, how much of the time was it positive and how much of the time was it negative. Okay, so this is all to say that we can actually characterize what the distribution looks like for the behavior in between visits to 0. And so how does this help us? Well, so now we're trying to understand how much of the time is this random walk above 0 and how much of the time is it below 0. And instead, we're going to alternatively generate a process where we generate a geometric random variable that tells us how many times did we return to 0 in the first place, and then what did we look like in between these return times. So the behavior of the random walk between return times will be distributed like t, but actually it won't be completely t. It has to be conditioned on the fact that we actually did return. So there's going to be a rescaling there. But basically, we can actually characterize what these random variables look like. Okay. And then this becomes very relevant in the analysis, not just of this teaching and learning strategy, but in other teaching and learning strategies that we discuss, is the behavior of this other process, mn. And so mn is going to be the number of +1s that were transmitted by the teacher to the student. So in the case when the student is a perfect student, so q is equal to 0, then we really just care what is the probability that mn is less than 1/2. Right? So we want to know when is the number of +1s transmitted by the teacher going to be bigger than 1/2 versus less than 1/2. In the case when q is not 0, we need to be a bit more careful, and I'll comment on that. Okay, but so we want to understand this object mn, and this object mn is defined in terms of these signs of the random walk in some way. So kind of the key point is that we're going to use some large deviations theory, and some of you may be aware of what's called the Gardner-Ellis theorem, which will give us actually these rates. It'll give us these probabilities in exponential units that some random quantity, some random vector, let's say, lies in a particular region. Okay, so the trick is that I've now shown you that you can turn this random walk xn hat, which we care about. We care about it in the sense of mn, right? We really care about some event that has to do with mn, which is a complicated function of xn hat. Actually, it's not that complicated. But what we said is that we can look at that object xn hat, and we can break it down into a bunch of different things. We can break it down into a geometric random variable, and also the behavior in between these return times to 0. These are these sojourns, these t's, and they can be positive or they can be negative. Okay, I'm already running out of time. Right, so basically the idea here is that we can break down the behavior of mn into some function of zn, and therefore we can rewrite the probability that mn is in this particular set on which we incur error in terms of zn being in a subset of the real numbers, actually R3, because it's a three-dimensional vector. And then we can actually calculate the probability of this event happening well, it's a calculation that has to do with the moment generating function of this vector. And sort of the beauty behind the mathematics of this is that we can actually calculate explicitly what the learning rate is. And lo and behold, it's something really simple. Turns out that the learning rate is delta times the KL divergence between a Bernoulli 1/2 and a Bernoulli P random variable. Okay. So fast forward a bunch. So when q is bigger than 0, when the student is not perfect, you have to be a bit more careful. And basically, you want to look at the probability that mn is in a particular range. And that's why, well, we case out the error event into mn being in a particular interval. But actually, this limiting probability that we can calculate in general, not just for is mn over n less than 1/2 or bigger than 1/2. We can characterize the probability that's in several different intervals. And then we can kind of look at the error event, the case that tends to dominate the error probability. Because we're interested in these learning rates. So we're interested in what is the behavior of the random walk of what the teacher observes that makes the probability of error the highest. And that will be the bottleneck for the rate of learning for the student. Okay, so then we can analyze the other methods using other complicated methods. So the last thing I wanted to say is just about Gaussian learning, where I said that everything kind of gets turned on its head. So in Gaussian learning, we have the state of the world, which is mu. And then we assume that the teacher observes noisy versions of the state of the world, where we're not going through a binary symmetric channel, but we're going through a Gaussian channel. Okay, that's a reasonable continuous analog of all of this. So the teacher observes IID observations y1 up to yn, which are normally distributed mu sigma 1 squared. And what does the student observe? Well, the teacher prepares his lesson. His lesson is xi, which is a function of what he's seen so far. And the student looks at her observations, which are noisy observations passed through a Gaussian channel. And then she calculates some kind of estimate. And the estimate is going to be a function of z1 up to zn, what she's seen so far. And what we want to do now is we also want to characterize sort of the rate of learning of these methods. But instead of looking at a rate of learning in terms of an error probability, what's the probability that mu hat is equal to mu? That doesn't really make sense in the continuous case. And instead, we characterize this looking at the variance. So if we imagine that she has to concoct some unbiased estimator of mu, then what is the right strategy that minimizes the variance of her estimator? And so one reason for looking at the Gaussian case is because things become much more simple, all right? So we can start to think not just about the weighting mechanisms where she puts equal weight on the last epsilon n time steps, but she could put any spectrum of weights on any time step, and you could plausibly look at the variance of what these estimators are, and that's exactly what we did. Okay, so we assume that the student can use any linear combinations of her observations so far. It could be all equal weight, 1 over n each, or it could be 1 over epsilon n for the remaining epsilon n, or anything in between. The teacher can transmit any linear combination of what he's seen so far. So A is this matrix that he's going to hit to his observation vector, and because his observations have to depend on the past, A is going to be a lower triangular matrix. And we also constrain the teacher to only transmit unbiased estimates. All right, and so the moral of the story is that we can, for a fixed teacher strategy, we can actually calculate what the optimal student strategy is. All right, so for any teacher strategy that we could care to pass through, we can see how we equally weight all of the observations as time goes on. And actually, the interesting thing is that we can also look at the jointly optimal solution. So this is something that we did not know how to do in the binary case because it was simply too complicated. And the really surprising thing is that when you minimize your variance, which is a function of the teacher strategy A and the student strategy B, an optimizer, we can't prove it's the unique optimizer. Actually, it isn't. Okay, so we can prove it's not the unique optimizer, but an optimizer is to simply forward and simple average. So the teacher should not do any work. It doesn't matter what these variances are of the noise. And the student should simply average what she sees. which is, well, I think quite surprising given everything I've been saying about the binary case so far. Okay? So that's basically it. So we've looked at a bunch of different teacher learning and teaching strategies. We have been able to calculate the precise learning rate of the student, and it's fairly complicated for all the settings except for the one that I mentioned, which was just the KL divergence. We also looked at the case of continuous states, and we showed that, in fact, the story is quite different there. And there are lots and lots and lots of other interesting ways to go with this. I think one information theoretically interesting way is if you have a broadcast channel instead, because a teacher teaches to a class of students rather than just one student, and to see how the learning rates of different students and the way that they aggregate their votes would affect their overall rate of learning. So thanks for your attention.